Okay, let's continue the second part for electromagnetic induction. In the previous session, we found that the inductance by the symbol L is found in this way, right? We found that the electromagnetic force, right, is equals to the change of the magnetic flux with respect to time, right? But we know that the magnetic flux, when we have a coil, is proportional to the change of the current, right? So we have that this magnetic flux with respect to time, this change is going to be proportional to the change of the current in that coil. Remember, we're dealing with this coil, right? And we created an back EMF. Remember that part from the previous session? Well, the same thing happened right here. We increase the current again. We increase the electromotive force, the back electromotive force. Okay, means again that this change in magnetic flux is proportional to the current. We increase the current, we increase the change in the magnetic flux. Okay, perfect. Means from here that electromotive force, right, created by this coil is proportional to the change of the current, right, with respect to time. How do we eliminate this symbol again? Well, using a constant. So in this case, it's going to be the electromotive force, right? So over here, right, is equals to a constant. The constant is L, right, times the change of the current with respect to time. L is called the self-inductance, or just inductance, right? So again, we create this formula that gives us, right, the electromotive force, the back electromotive force right here. Okay, perfect. L, the inductance, delta I, the change in current, right, respect to time. Got it? Okay, perfect. Now let's go to the next topic, right? The next topic is gonna be the AC generator, right? AC generator. AC generator, or just alternator. Okay, this AC generator, right, consists of a constant magnetic field, right, and we have a coil, right, that rotate inside of this constant magnetic field. Okay, means again that we are we're in the case that we create current when we rotate, right, the coil inside of this magnetic field. Remember, that's the third way how we create current, right, according to the previous session. Okay, perfect. Now let's see what happens. In this case, we have electromotive force is equals to, right, numbers of turns, remember, times the change of this magnetic flux with respect to time. But how do we define the magnetic flux? Remember from previous section, we have the magnetic flux, right, is equals to area, right, the magnetic field intensity cosine theta. Okay, in this case, we are changing the angle. This area, the area of the coil, right, is constant, right? The magnetic field is constant, so we're changing only the angle. So it means what? That the electromotive force is equals to N, right? We can use negative according to Faraday's law, Lenz's law too, right? Equals to, well, this constant, we change only the angle. So it's gonna be A, B, right? Change cosine theta, right? Respect to time. Got it? Okay, now let's see what happens with this change. Okay, the change of cosine theta, we use calculus to make it faster. Let's use some calculus. Okay, this class is not calculus based, but okay, let's use some calculus to make it faster. Theta, remember, is right to omega. Omega, remember, is equals to theta divided by time. So from here, right, theta is equals to omega t. So we can say then that cosine theta also is equals to cosine omega t, right? Got it? Okay, perfect. Now let's find the change of this angle respect to time. Remember, because we're dealing with respect to time, so let's go respect to time. So from calculus, this is, okay, the derivative of cosine omega t respect to time is equals to negative, right, omega sine omega t. Right? We can do this without calculating. It takes for a long time. In this case, we don't have too much time. Okay, let's take this as the change. Okay, now when we go back to this equation, right, we found that this is equals to let me do it where, okay, let me do it right here. This is equals to electromotive force is equals to, right, n a v omega, right, sine omega t. Right, this is for an AC generator, correct? But because of omega right here, because this is constant, and this angular velocity is also constant, right? This factor is also a constant. So we can represent this in general. The electromotive force equals to some constant, right? Epsilon naught, let's say, times sine omega t. So that's the final equation that we can use right here, right? Electromotive force equals to this maximum peak, right, times, or the amplitude, right? The amplitude times sine omega t. Okay, that's the equation that is used for a AC generator, where we are making this depends on time. As you can see, this is voltage, right? So what happens to voltage? Voltage is, right, a sine wave. The voltage that we have right here in the houses, right, is oscillating, right? Is the electrons, right, are oscillating back and forth, just alternating current, remember? Back and forth. So produces like a harmonic motion, right? A spring, which behaves also in this way. Correct? Okay, perfect, great. Now let's move to the next topic, right? The next topic is gonna be the energy stored, right? Yes, in a inductor. Remember, when we're dealing with charges, like with electric field, we found that we have this device, right? These two plates, right? One is positive, right? And the other one is, right, negative charged. We found, right, that this, which is, we call the capacitor, right? The capacitor stores, right? It stores charge, right? Positive and negative, right? It also stores, right, electric energy, and also store what? The electric field. Remember, we have electric field over here inside. So this simply happens when we're dealing with a magnetic field, right? We can storage, right, the magnetic field using this inductor. So the function of the inductor is to store, right, magnetic field. Okay, now let's try to find the energy that also is stored on this inductor. Okay, let's do it. It's like right here, right? The energy stored in a capacitor was found. Let's do the same thing for the inductor. Let's try to find, right, the energy stored in the inductor or by the inductor. Okay, let's do it. Remember, how do we define the electromotive force, right? Electromotive force, right, produced by the inductor. Well, let's define it this way, right? Electromotive force is equals to the inductance times the change in current respect to time. Okay, but in many cases when the change is not constant, right? When the change is constant usually, right? Or changes in time, right? The change of the quantity, we can use the average, right? Like in this case, right? Instead of taking, right, this is equals to current, right, at the end minus current at the beginning, which is 0, at the beginning 0, then we have the maximum current right here for this delta I, right, divided by delta T, right? Instead of taking this final current, because it changes in time, right? Let's take the average, right? We can solve it using calculus again, but this is not calculus based, this is algebra trig based, right, lecture. So let's take the average, right? So we have that the electromotive force, right, the average, right, is equals to the inductance times current, right, divided by 2, correct? That's the average of the current, also time right here, right, divided by time, 2 time. Okay, perfect. Now let's go to the equation that gives us energy. Energy is related to power, right? Power, remember, is defined as work. We can use work, or we can use energy, right, per time. In this case, we can say that energy, right, is equals to power times the time, correct? Okay, perfect. Now, but how do we define power? Power, let's use average, right? The average power, okay, average power is equals to current average, right, times voltage, right? Current average, okay, let me go right here. This is T, this is equals to what is the average? The average is gonna be average current times voltage times time, correct? Now, because the voltage right here is the electromotive force, right? Voltage is the same as electromotive force. Okay, it's subject to this value right here. And what do we have? We have right here that the energy is equals to average current times the electromotive force, which is L current divided by 2T, right, times time. Is found right here that the energy, right, is equals to current average. Also, it's gonna be average, right? Current average right here, average, right, square times L, right, divided by 2. So this is the energy stored in the inductor. So the energy stored in the inductor is equals to, okay, inductance current square divided by 2, right? Divided by 2. Again, this is the average current. Got it? One more time. This is remember that the average for the energy for the capacitor was capacitance, right? Charge divided by 2. Right? They have the same form. You can check this on formula sheet. Correct. Okay, and this is again the energy stored in a inductor. Remember, this is the inductor. This is one of the elements of a circuit. Remember, the elements is what? The inductor, right? We have the capacitor, right? And we have the resistor. Remember, these are the elements, the main elements that so far we have, right, in a circuit. Also, we have, right, the battery, and we have also the generator, right? This is battery. Remember, this is a capacitor, and this is a resistor. It's gonna be the generator. It's a wave, right? The symbol is a wave, right? Because it's oscillating, right? So the current oscillates, the same thing as the voltage. Correct? Okay, great. So in the last topic for this chapter is gonna be the transformers. Okay, let's go to transformers. Great. Okay, perfect. Let's go to transformers. Okay, transformers are devices, right, that changes the voltage, right? Change the voltage in in a circuit. Let me give the definition from your book. It says transformers. Transformers. Okay, a transformer, right, is a device for increasing, right, used for increasing, right, or decreasing, right, a AC voltage, a AC alternating, right, current voltage, right. And we have two types of transformers again, one that increases and one that decreases the voltage. Okay, so again we have transformers, right. We have two types. One is called the step up and the one step down. Step up, right, and step down, right. A step up transformer just increases the voltage, right? Increases, right, voltage. Okay, voltage. And step down is the opposite, right? Decreases, right, voltage. Okay, this is the picture for the transformers, right? We have this picture. We have a this is the core. Usually it's iron core, right? Something like this. Imagine. And then we have, right, the coil, right, like this. Imagine. These are connected to a AC source, right? This is AC source, right? To have the voltage right here. We call this the primary numbers of loops or coils, right? Okay, this is N and P, right? Primary, right? Number, right, of coil, right, or loops. VP, right, is called the primary voltage. V, right here we have again the induced voltage, right? So we have right here, this is called the secondary voltage, and we have the secondary, right, number of turns. Okay, now when we use Faraday's law, right? When we use Faraday's law, remember Faraday's law creates primary, okay, voltage. When we use Faraday's law, remember it says the electromotive force created by these two inductors, right, is equal to negative N, right, change in the magnetic flux divided by time. Okay, so we have magnetic flux right here, we have magnetic flux right here. Okay, because of conservation energy, right, these two are supposed to be the same, correct? So what do we have for case one? For the primary case, right, usually we don't use this one, we use voltage, right? Voltage for primary case is equals to negative NP, right? Times what? Times the change in the magnetic flux respect to time. For the second case, or second numbers of loops, right, the secondary voltage is equals to negative NS, right? Change in the magnetic flux respect to time. When we divide these two, this sign is cancelled, and also these two are cancelled because they're supposed to be the same because of the conservation of energy. Okay, perfect. Now what do we have then? That Vp over Vs is equals to MP over ns. Right, right here we solve for any quantity we're looking for, right? And we get, right, the voltage. Imagine we're looking for the secondary voltage, so it depends on what are the primary voltage and depends on the numbers of turns for each case, right? So we have this equation that gives us, right, the relationship between voltage, right, that is related to the numbers of turns, right, on these inductors, right, or coil, correct? Okay, perfect. Now let's see what happens when we involve the current. Okay, when we involve the current, the same thing as before, right? We have that power. Now let's go to power, right? Let's go to power. Power is equals to current times voltage, right? We call this the power created by these numbers of loops, right, in the primary, right? Because power is related to energy. Remember, power is equals to energy divided by time. If energy is conserved, this is a special case, right? When energy is conserved, right, the power created by this generator is the same power, right, that is induced in the second coil, right, because of conservation of energy. Okay, if that happens, if we call this the power in the primary, right, it's gonna be the current in the primary equals to the current in the primary times the voltage in the primary, right? If we do the same thing for the secondary inductor, so this is equals to the secondary the current secondary coil, right, times the voltage in the secondary coil. Okay, the same thing as before. If we divide this divided by this, because these two are the same, right, this becomes 1, so 1 is equals to current, the primary, current, secondary, right, and voltage primary, right, voltage secondary, correct? Okay, when we arrange this, what do we have? Look, we have that we are looking something like this, right? Let's try to look something like this. So Vp over Vs. Okay, let's solve for this one. So what do we have? Vp over Vs, or primary voltage, secondary voltage, is equals to, right? Is equals to current, secondary current, right, by primary current. But this is the same as this, and it's the same as this, so it's equals also to, right, current, the secondary coil, divided by current, the primary coil. Correct? Okay, this is the general equation, right, for transformers. Right, we play with this to get, for example, how many turns do we need, right, to create, right, as at the end, for example, secondary voltage. Once we know the primary voltage, what should be the relationship between the numbers of turns, or what should be, right, the relation for the current. So this formula works for any case where we're dealing with transformers. Okay, and with this we finish the this chapter, electromagnetic induction, right, the second part. Okay, see you in the next chapter.